Hi everyone. So in the last class we have seen properties of real numbers under addition, multiplication and order axiom. So in this class let we see a field. Okay. So to define field we need these properties. Those are your closure law under addition, associative law under addition, existence of additive identity under addition, existence of additive inverse under addition, and commutative law under addition. And your next laws are closure law of multiplication, associative law of multiplication, existence of multiplicative identity, existence of multiplicative inverse, and commutative law of multiplication, as well as distributive law. So using these conditions we are going to define a definition. So that is a non-empty set with at least two elements in it and with two binary operations. Those are plus and multiplication, satisfying all the above 11 axioms. Those are A1, A2, A3 and A5, as well as M1, M2, M3, M4 and M5. Already I have given the definitions of all those and your distributive law. So these all conditions holds good, then we call that as a field. So your R plus dot becomes a field. So we can call therefore R plus n dot, that is multiplication, is a field. So next definition is, that is, if a field satisfies all the four order axioms. Those are your law of trichotomy, okay, the law of trichotomy law, as well as monotone law of addition, next transitivity law and monotone law of multiplication. If these all axioms holds good, so then we call that as ordered field. So you remember these things in your mind, okay? So one is R plus dot is a field and next is ordered field, okay? So next let me see some of the examples based on your real number system, okay? So that is, prove that in the set R of real numbers, first condition, that is additive identity is unique. So next is multiplicative identity is unique. Next is additive inverse is unique. Next multiplicative inverse is unique. So now I will give a solution for your all four conditions. So first let me see additive identity is unique, okay? So for that I take, so 0 is the identity element under addition. So here I take two identity element and I have to prove using those two identity element. Is 0 is equal to 0 dash, means this is also identity element and this is also identity element. So if 0 equals 0 dash, then your given question, that is additive identity is unique, holds good, okay? So here I am taking, let 0 and 0 dash be two additive identities in R. So here I take, so there if we write A plus 0 is equal to A, there 0 becomes identity element. So in place of A I am taking here 0 dash. So therefore 0 plus 0 dash is equal to 0 dash. 0 plus 0 dash is equal to 0 dash. So here what we get, 0 as the identity element. So in place of A I am taking 0 dash, okay? So then here 0 plus A is A. So here 0 plus 0 dash is 0 dash. Therefore 0 is the additive identity. Also 0 plus 0 dash is equal to 0 dash. 0 plus 0 dash is equal to 0. So here we are getting 0 as, so here we are getting 0 dash as the additive identity, because 0 plus 0 dash we are getting the result is 0. So here becomes 0 dash is the identity element. So in this case 0 is the identity element. So in this case 0 dash is the identity element. So but these two are equal to each other. So but 0 plus 0 dash is equal to 0 dash plus 0, because 0 dash plus 0. Okay, so therefore 0 plus 0 dash is 0 dash, and 0 plus 0 dash is 0. So 0 plus 0 dash is 0, and 0 dash plus 0 is 0 dash. Therefore the additive identity of 0 is unique in R. So next, multiplicative identity is unique. So let me see that. So here also we take two identity elements, those are 1 and 1 dash, be two multiplicative identities in R, as 1 is the multiplicative identity we have. So if your 1 becomes multiplicative identity, so then we can write 1 into A is equal to A for all A belongs to R. Okay, so in the place of A as 1 dash, then we get 1 into 1 dash is equal to 1 dash. 1 into 1 dash is equal to 1 dash. So in the place of A, I am replacing the value of A as 1 dash, then your equation becomes like this. Okay, so again 1 dash is the multiplicative identity. 1 dash is the multiplicative identity. Then we have 1 dash into A is equal to A for all A belongs to R. So here I take A is equal to 1. Then this equation becomes 1 dash into 1 is equal to 1. 1 dash into 1 is equal to 1. So from these two equations, because here 1 into 1 dash is equal to 1 dash, and 1 dash into 1 is equal to, these two are equal. Okay, so but here 1 dash equals 1. 1 dash equals 1. So therefore the multiplicative identity under real numbers is unique. Multiplicative identity under real numbers is unique. So because here we are getting the equation by equation 1 and 2, we are getting the result as 1 dash is equal to 1. 1 dash is equal to 1. So next, additive inverse is unique. Let me see the solution of additive inverse is unique. Additive inverse is unique. So here I am taking, let there be two real numbers B and C such that, so here A plus B is equal to 0. So here your B is the additive inverse and A plus C is equal to 0. Here C is additive inverse. So we have to prove B is equal to C. Then your additive inverse is unique. B is equal to C, then your additive inverse becomes unique. So here I am taking the equation as, now B is equal to 0 plus B. 0 plus B. So here 0 is the additive identity, because 0 is the additive identity. If we add, then we get B. Okay, so here in the place of 0 I am taking this A plus C plus B, because A plus C is 0. A plus C is 0. So I am writing A plus C as C plus A because of additive commutativity. Using the law of additive commutativity, so I am writing A plus C as C plus A plus B. So this is equal to C plus, using associative law, I am writing this as C plus A plus B. C plus A plus B. So because of additive associativity. So A plus B is what? 0. A plus B is what? 0. Because of A plus B is equal to 0, I am writing this as C plus 0. Because of additive identity, it will become C. Hence, B is equal to C, which proves the result, that is additive inverse is unique under R. So next, multiplicative inverse is unique. That also we have to prove. So here I am taking, let there be two multiplicative inverses that are B and C. So here A should not be equal to 0, belongs to R, such that A into B is equal to B into A. A into B is equal to B into A is equal to 1. So here your multiplicative inverse becomes what? B. So A into C is equal to C into A. Okay. So here your multiplicative inverse becomes C is equal to 1. So here I have to prove your both multiplicative inverse are equal to each other. Okay. Equal to each other. Then your result, that is multiplicative inverse is unique. That holds good. So now I am taking here B is equal to 1 into B. So B can be written as 1 into B because of multiplicative identity. Okay, if you multiply by 1 using multiplicative identity, you can write B. So here I am taking in the place of 1 as CA. Okay, because CA is equal to 1. So that I have already written here. So using multiplicative associativity, I am writing this as C into AB. Okay, C into AB. So AB is equal to what? 1. Already given that here. Because of AB is equal to 1, I am writing this as C into 1. Using multiplicative identity, I am writing this as C into 1 as C. Hence, B is equal to C, which proves the result. So here we have proved your 4 results. Those are under the set of real numbers. Your additive identity becomes unique, multiplicative identity becomes unique, additive inverse becomes unique, multiplicative inverse becomes unique. So you remember these results. Okay, these are very important. Okay, so next that is, if A plus B is equal to A plus C, then prove that B is equal to C. So solution for this is, we have B is equal to 0 plus B. So I am taking here B. So using additive identity, I can write this as 0 plus B. So here I am taking additive inverse as minus A plus A. Using minus A plus A becomes 0. Okay. So using additive associativity, I am writing this as minus A plus B. Minus A plus B using additive associativity. So later it becomes, so your A plus B is what? A plus C, because already given data, that is A plus B is equal to A plus C in your question. So then it will become minus A plus C. Next, using additive associativity, I am writing this as minus A plus C. Minus A plus A becomes 0 because of additive inverse. So your 0 plus C becomes C using additive identity. Hence, A plus B is equal to A plus C. That implies that B is equal to C. So your next result is, if A into B is equal to A into C, then prove that B is equal to C. Here A should not be equal to 0. So we have here, I take B. So using multiplicative identity, I can write this as 1 into B. So you already know that using multiplicative inverse, I can write A inverse into A is equal to what? 1. Okay. So using multiplicative inverse, I can write this as A inverse into A is equal to A inverse into A into B. Okay. Using multiplicative associativity, I can write this as A inverse into AB. But AB is equal to what? AC, given data. So A inverse into AC. So using multiplicative associativity, I can write this as A inverse into A is equal to A inverse into A into C. But A inverse into A is equal to what? 1, using multiplicative inverse. 1 into C is equal to what? C, because of multiplicative identity. Hence, A into B is equal to A into C. That implies that B is equal to C, which proves your given example. Okay. So if you have any doubts regarding these examples, okay, you can ask questions. So for your definitions, you see all the laws. Okay. So then you can understand what is the meaning of field and ordered field. Okay. So with this, I conclude this class. If you have any doubts regarding this, you can send questions to my WhatsApp number and clarify your doubts. Thank you.